Oblique asymptotes. For simplified rational functions, r of x equals p of x divided by q of x, and the degree of p of x is equal to the degree of q of x plus 1. So the degree of the numerator is equal to the degree of the denominator plus 1. So the one on top is one more than the one on the bottom. So for simplified rational functions like that, oblique asymptotes are the lines y equals mx plus c, where m does not equal 0, that the function approaches as x tends to infinity or negative infinity. So in other words, this simplified rational function here gets closer and closer towards looking like the line y equals mx plus c as x tends to infinity or negative infinity. So it's just like horizontal or vertical asymptotes, except this time it can be just an arbitrary line. So it can have a gradient that's not equal to 0. By the way, I don't know why I wrote simplified here. It works for non-simplified as well, because if p of x divided by q of x is a non-simplified rational function, you can just simplify it by dividing out all the common factors. Alright, so they're called oblique asymptotes because they're not horizontal or vertical. Not horizontal or vertical. It's an arbitrary line y equals mx plus c with a non-zero gradient. Now, to find the oblique asymptote, we can use polynomial division to write p of x divided by q of x equals mx plus c plus s of x divided by q of x, and in this case the degree of s of x is less than the degree of q of x. So that means that s of x divided by q of x is equal to, let's say s of x is a0 plus a1x all the way up to m x to the power of m, and then q of x can be b0 plus b1x all the way up to bm x to the power of m, and then it keeps going all the way up to bn x to the power of n, where n is bigger than m. And then if we allow x to tend to either positive infinity or negative infinity, let's just say the absolute value of x tends to infinity, then since n is a larger natural number than m is, this bn x to the power of n term really is all that matters. Because if you're taking a really large number to a higher power, you're going to get something that is much bigger. And so, as a result, the entire fraction tends towards 0. So this whole fraction tends towards 0 as the absolute value of x tends towards infinity. And so since this thing is going towards 0, that means this thing must get closer and closer towards the part that isn't going towards 0. So p of x divided by q of x tends towards mx plus c, the oblique asymptote. So, how do you find oblique asymptotes? Use polynomial division. Now, a little exercise at the bottom here. What happens if the degree of p of x is equal to the degree of q of x plus n, where n is bigger than 1? So you should pause the video and have a think about that. Well, if the degree of p of x is equal to the degree of q of x plus n, where n is bigger than 1, then all that means is that when we do this exact calculation here, we're going to end up with some polynomial instead of a straight line to replace the mx plus c. So we'll have some polynomial, let's say w of x, where w is a polynomial, and the degree of w is going to be n. If you're not convinced that the degree of w is equal to n, you should pause the video and try and prove it. Well, one way to see that the degree of w has to equal n is to take this whole equation here and times both sides of it by q of x. And so you would end up with p of x is equal to w of x times q of x plus s of x. And note that the degree of w of x times q of x is equal to the degree, so let's say the degree of wq is equal to the degree of w plus the degree of q. And we also know that the degree of s is less than the degree of p. Sorry, the degree of q, which is less than the degree of p. So the point is the degree of s is less than the degree of p. And so it must be the case that, well, the degree of p is equal to the degree of w plus the degree of q. Degree of w plus the degree of q. And therefore, since the degree of p is equal to the degree of q plus n, it must be the case that n is the degree of w. Anyway, that exercise wasn't completely related to what we're talking about, but the point is we're going to end up with, if the degree of p of x is equal to the degree of q of x plus n, where n is some number bigger than 1, that's going to be the degree of the polynomial that we end up with in place of the mx plus c. And so p of x divided by q of x in this situation would get closer to some degree n polynomial w. Wait, that's not usually the way I would write that. Let's see. Degree w equals n. We can try a few of them out in Desmos. I encourage you to pause the video and do that. Alright, let's consider r of x equals 3x cubed plus 2x squared plus x plus 1 divided by x plus 1. Real original, I know. So let's go ahead and do our long division. X plus 1 into 3x cubed plus 2x squared plus x plus 1. And we multiply it by 3x squared. So that gives us 3x cubed plus 3x squared. So then negative x squared plus x plus 1. And then we multiply it by negative x. So that would give us negative x squared minus x. And then we get 2x plus 1. So then plus 2. And then just finish it off for fun. 2x plus 2 gives us negative 1 as a remainder. And so that tells us that 3x cubed plus 2x squared plus x plus 1 is actually equal to, oh, sorry, for this purpose it's better to keep it as a rational function. So divided by x plus 1. So this rational function is equal to 3x squared minus x plus 2 and then it's minus 1 divided by x plus 1. And we can see that the 1 divided by x plus 1 tends to 0 as x tends to plus or minus infinity. And so the whole thing, the rational function r of x, which is equal to this thing, r of x should tend towards 3x squared minus x plus 2 as x tends towards plus or minus infinity. So let's go ahead and graph it in Desmos and see if we're right. Alright, so just open the browser, www.desmos.com, graphing calculator, loading a bit slowly today. Alright, here we go. Okay, so the function was y equals 3x cubed plus 2x squared plus x plus 1, and that was divided by x plus 1. Alright, so we get this kind of wonky looking thing. And we said that it should get closer and closer towards 3x squared minus x plus 2. Now looking at this thing, it looks like I made a mistake. Well, on this side it seems okay, because as x tends towards positive infinity, it looks like it's getting closer. But as x tends towards negative infinity, what's going on? It seems to be varying drastically. But luckily, if we zoom out a bit further, we see there's more to this function. There's actually a vertical asymptote at x equals negative 1, and then the function picks up after that. And as it goes towards negative infinity or positive infinity, we can clearly see it gets closer and closer to this 3x squared minus x plus 2 parabola. So yeah. And to finish off this video, here's one more example. We have our rational function r of x, and in this case the degree of the numerator is equal to the degree of the denominator plus 1. So degree of p of x is equal to degree of q of x plus 1. And I'll leave it to you to use polynomial division to show that r of x is equal to x plus 3 plus some remainder polynomial s of x divided by x minus 4 times x plus 1, where the degree of s is less than or equal to 1. So that would make this whole term go towards 0 as x tends towards plus or minus infinity. And hence we have the oblique asymptote, which is this one here, y equals x plus 3. Oblique asymptote. And note one other point of interest here is that this function, so the function r of x is the red curve, and note that it actually intersects its asymptote. R of x intersects its asymptote. To find the point of intersection, you can simply set r of x equal to the asymptote, equal to x plus 3, and then solve for x, and that'll give you the point of intersection.